I'm Lee, and from work as a postdoc at DTU. Currently, I work together with Professor Pierre Pinson on a project about district heating systems. So today I'm going to introduce part of our work on the topic of online short-term forecasting of aggregated heat load. First, I would like to introduce a bit about the background and motivation. So currently, many countries have committed to achieve carbon neutrality goal by 2050. So has the Danish government. This brings new reforms and change in different sectors. So in the heat sector, one of the main reform is to accelerate the process of electrification. And in this heat sector, the low temperature heating system are considered as a cost-effective, energy-efficient technology for heating supply. Usually, they use like diverse green energy such as surplus heat and geothermal heat for heat supply, and they can be helpful to integrate more renewable energy generation into power grid as well. So in the current district heating sector, the supply of heat is a natural monopoly. This is due to the economies of scale for both heat production and network cost. So the network cost involved is prohibitive, that there's usually one provider for an area, and the heating supply is controlled completely by the consumer's demand. And the heating price in the Danish heat sector is flat regardless of time, and they're not the same for all the areas. And in principle, the heating price is determined by the law, which can guarantee all the related costs can be covered by the payments from the consumers. So above all, in the whole process of electrification, the heating system can serve as a load for power grid, which could potentially provide flexibility from heat demand side to power grid. So in this way, it's very important to understand the heat consumer behavior and propose a different heating price scheme to incentivize consumers to change their behavior and thus unleashing the flexibility from the heat demand side for power grid. So in this work, our objective is to make a day ahead hourly load forecasting. There are two main challenges in our project. The first challenge is a very practical one. As the heat sector is under great transition, the digitization system are being upgraded. So currently we only have hourly data. In the near future, we will have very high time resolution data, such as 5 minutes. So this online heating load data call for online methods. On the other side, the heat load time series is non-stationary and non-linear. To cope with the challenges, we propose online learning methods together with nonlinear transformation to capture non-stationary characteristics of the online heat load data. The next part is about the data we used in this work. It is from a Danish island, which is Bornholm Island. The aggregated heat load data are from around 4,000 meters, including residential building, office building, and etc. And the whole time duration is 1.5 years from the January 2019 to the June 2020. And the data is hourly data. So in this figure, we can find the heat load time series non-stationary. That's motivates us to propose online methods to adapt to that. Besides the heat load data, we have weather forecast data, including temperature, wind speed, solar radiance, and the humidity. So in the following, I'm going to present some features about the heat load time series. So in the figure on the left side, it presents the heat load is highly correlated with its own 1 hour lag data series. On the right figure, it shows the frequency spectral, which display a strong daily periodicity of heat load series. Therefore, we consider 24-hour lag data as input feature for our online learning methods and on a daily basis. This is a scatter plot about heat load and all the weather variables. Here, the blue color refers to the data in the heating season, which from the October to next to May, and the orange refer to non-heating season. In our work, we focus on the heating season data. Besides, from this figure, we can find that the temperature is much more highly correlated with heat load than the other three weather variables. So the next part is about methodology. We apply two nonlinear transformation of the heat load time series. And so apart from the weather variables and constant factor as input, we use the nonlinear transformed 24-hour lagged heat load data as input. We propose online learning algorithm under two frameworks. The first is recursive least square framework, where the regression parameters are determined by minimizing a weighted least square error cost function, and a recursive solution can be found. The other is recursive maximum likelihood framework, in which the output is assumed to follow Gaussian distribution. So here, the regression parameters and the model variance are determined by maximizing a weighted likelihood cost function, and a recursive solution can be built by using Newton's method. In this work, we consider both point forecasting and probability forecasting. Therefore, we use different benchmarks. For point forecasting, we used persistent model, ordinary least square model, and OLS model with two nonlinear transforms as benchmark. For probability forecasting, we consider OLS with the empirical estimation, the probability forecasting, and the other three empirical models as a benchmark. So for the online learning algorithm under recursive least square framework, they provide point forecasting directly, and their corresponding probability forecasting are made by estimating the various forecasting errors empirically. The online learning methods under RML framework directly provide both point forecasting and probability forecasting results. Two hyperparameters are included in the online learning methods, which are forgetting factor and transformation parameters. Those two parameters are selected by using the lowest root mean square error of the validation data set as a criteria, and the results are presented in this table. So with the already found optimal hyperparameter parameters, we analyze the results for both point forecasting and probability forecasting in the test data set. So in those two figures, we show the probability results related to one offline method of OLS and the other of online methods for RML. But we still look at this figure, we find the quantile intervals are narrower on the right side, but we still need like more specific metrics to evaluate the performance. So in the following, we consider three metrics for point forecasting evaluation, which are RMSE, MAE, and MAPE. For the probability forecasting, we consider CRPS as a metric. These three metrics provide similar information. So due to the limit time and space, I only present the results related to MAPE. And from this figure, we find the lower errors are located in the middle, which are referred to the online methods. This indicates online methods perform better than offline methods. Look at the first three bars, and we found they are even higher than the persistence model. So in this case, we found a persistence model in our data set is a very strong benchmark. And among all the online learning algorithms, we noticed that the yield-adjusted nonlinear transformation gave rise to the worst performance. Since the proposed online learning algorithms are updated on a daily basis, so we need to look into the details about the performance regarding lead time. So in this figure, we can find the online learning algorithm under RML framework are consistently better than those under RLS framework. In addition, we can find that the Yale-Joseph transformation performs worse than the other online learning methods, especially in the daytime hours. For the probability forecasting evaluation, we use CRPS and define a skill score by considering the CRPS of OLS as a benchmark. So if the skill score is positive, it indicates the method performs better than OLS, otherwise it is worse than OLS. So from this figure, we can find the empirical models are worse than OLS method, and most of the online methods performs better than OLS. And among all the online learning methods, we can find the online learning methods under RML frameworks are consistently better than those under RLS framework. Again, this figure is about the skill score with related to the lead time. We can see more details here. We can find the online learning methods with Yale-Joseph transformation performs worse than the other online methods. And we can still find like RML methods perform consistently better than RLS methods. So in the total, we can find the RML, which is the which is the purple color, performs the best. To wrap up our work, we can draw such conclusions. The first, for our data set, online learning methods are better than offline methods because online learning methods help to capture the non-stationary characteristic of heat load time series. In addition, all the online learning methods under RML frameworks are better than those under RLS framework. And the largest normal transformation can be helpful to stabilize the variance for the heat load time series. So in the future work, we will apply online methods for very short-term heat load forecasting, and we will also work on the hierarchical probability forecasting as we have diverse data for the whole island. And we will apply our proposed probability forecasting model for the heat demand response related optimization problem in the future as well. Thank you all for your time. And if you have any questions, you still have time to ask.
Hi, yeah, first of all, thank you for your nice presentation. I actually have a short question. Did you do the demand forecast aggregated or on individual levels? So for one household or?
Right now, I'm doing the aggregated one.
Okay, aggregated. In the last slide, you said you want to do it for every household, or?
Excuse me, can you just?
You want to do the forecasting for every household? Hierarchical probabilistic forecasting.
Yeah, right now this is about the aggregated one, but for the future work, we will consider the individual forecasting. I mean, it depends. So the individual forecasting can be defined based on, based on different zone, or can be defined based on the different kinds of consumer, just like you mentioned, like for residential buildings or office buildings. So I think this will be part of our future work.
Mm-hmm. Okay, great.
Okay. Any more questions? Then, yeah, I'm not quite sure. We could maybe wait 2 more minutes until we continue in case some listeners will enter for the next session. And so then let's continue.
I could ask a question to Lee.
Yeah.
Thanks for the presentation. The results you showed, these curves, you know, of the forecast performance as a function of the lead time earlier in some of the previous slides, you know, it's kind of wavy, and it's getting, yeah, voila. So it's getting better in the morning, and it's kind of worse at midnight, for instance, or in the afternoon. Is this an effect due to the MAPI, the fact that you measure that you normalize by the measurement, right? Because I guess that's the point, right? That during the night and the afternoon, there's less consumption. And so that's why when you divide, somehow that makes the MAP higher. Is it the case?
I mean, just curious, like, do you mean why the level of the MAP are different for different hours, right?
Yeah, the fact that it's quite high actually for midnight to 3 in the morning, say. Don't you think it's due to the fact that you, by normalizing by the actual measurements, and the measurements are quite small, then it makes the MAPI quite higher?
I think I think it could be a reason, but I need to look into that.
Yeah.
Thank you for your question.
Yeah, my pleasure.
So, okay, I guess we could continue with the next talk. So, okay. Then
I believe it's me. Yeah.
Yeah, exactly.
Okay, so I can start by sharing the screen and waiting some minutes maybe. Okay. So you can see my screen, I believe. Yes.
Yeah.
Okay. So can I start, or we are going to wait a little?
That's fine. We have 20 past and we are ready to go.
Okay. So my name is Eralda Gica. In this study, I'm presenting with my 2 colleagues, Enzo Lamberti and Dule Basha, a study we've done about the prediction of energy production by hydropower using machine learning algorithms with priority weights. This is a case study for Albanian. So the main objective here is to analyze and then to build an accurate prediction model for the total energy produced by the 3 main hydropower, which are positioned in one of the largest river in Albania. So here you can see the position of the 3 hydropowers, starting with the largest one, and then continuing with the second, and then the third. And then there are also some other hydropower plants which are less important, let's say, in the amount of production. So this is a view of the hydropowers by the top. And in fact, the main reason why we are focused on predicting the production of the energy is the fact that Albania is now, from December of the last year, it is now as so selling energy in the market, which was not, let's say, used before. So the Albanian Ministry of Environment expects that approximately in 2025, the situation of the energy production by the hydropower plants will be almost so 23,000 gigawatts per hour. So in this study, in fact, we have analyzed the energy production based on some other regressors. External variables, which are the average temperature, the monthly average temperature, the average inflow in the first hydropower, which was then used as an inflow for the second and the third hydropower. And then the average rainfall, monthly rainfall, and the period taken into consideration is from 1991 to December 2016. So in total, there are 312 observations. So the situation, in fact, is based mostly in the seasonality patterns of the average temperature, which is clearly seen in Albania, and also the average monthly rainfalls, precipitations. And in fact, based on these two seasonality, you can also see the seasonality pattern of the cascade production. This is the total amount of energy produced in the whole cascade, so in both, in all the three hydropowers. And this is in fact 1 year, which is due to the changes in the legislation, so in the rules of the energy production in Albania. So maybe this is something we need to consider. And what we have done in our methodology. So we have based our predictions in a forecast combination model. So in our methodology, we propose to give a weight to each of the models, and then to use the prediction taken from all the models we propose, and then to construct an ensemble model. So there are, in the literature, you can see there are a lot of methodologies which are adopted to estimate the weights. And in fact, what we have used is maybe a little different from the other studies. So based on many studies and many competitions, such as the M competitions, we know that statistical combination of forecasts will improve forecasting accuracy in most of the time. And then a combination of the statistical, so classical time series models and machine learning prediction models are more likely to generate accurate forecasts. So if we compare them only with the machine learning apart and then the statistical method apart, but if these are also associated with a human judgment, they are likely to be a great weapon. So they will give us a more accurate prediction in the future. So where is based our methodology? In fact, what we do is not something, let's call it, it's not something special, but in fact, we start by constructing statistical models and then also machine learning models to our data. In fact, we have the opportunity to use those models which are mostly accurate for monthly time series. So in fact, here, what we do is we analyze the performance of the models based on the in-sample and out-of-sample data. So our focus, in fact, is to obtain accurate predictions for the out-of-sample data. I'm showing to you later a chart of the methodology, but I will stop here just to give you some information about the classical models we have taken into consideration and the machine learning model. So we start by constructing simple exponential smoothing models, ARIMA models, machine learning models, or neural network models, or other combinations of them. And in fact, what we do is, after we construct these models, we calculate the correlation, the Pearson correlation coefficient. So just to understand the correlation between the real data, so which we have, and those fitting data, so for the in-sample and the out-of-sample data. And then what we do, after we construct these models, we are using the least square support vector machine to obtain the final model, let's call it like this. And the objective of the methodology is to minimize the errors, and then the coefficient of the model, so the model will look like this one here, with the constraints that the sum of the coefficients for each of the models, so these are a kind of weight we give to each of the model. The sum of this weight is equal to 1 because it gives a kind of a percentage of the contribution of each of the model to the final prediction. And of course, this weight should be positive. We've used many accuracy measurements, such as the error measurements here, and also information criteria. So after we construct these models, we start by analyzing these accuracy measures to select the, let's say, the ones which are more accurate for prediction. And then we also use the correlation coefficients. So we know that the Pearson correlation coefficient can be a good measure, let's call it like this, for estimating the linear correlation between the two variables, in this case, the real data and the predicted data, even if it has other disadvantages, which we are looking for to understand and to, let's say, to eliminate and maybe to substitute with another measurement. So this is our methodology flow chart. So we start with our target time series and the other explanatory time series, which we are going to use. So in our case, the target is the energy production by the total cascade. And the explanatory variables are the rainfall, the temperature, and the inflows. So then we go through the classical steps of preprocessing the data and starting by using statistical models and machine learning models. And then after we estimate, so after we go through these phases of identification, estimation, and validation of all these models, we decide which of the models to accept, so for considering later, and which one do not accept, and maybe go back and try to construct some other models. So for those models which we call acceptable, so they have a considerable accuracy in the in-sample and out-of-sample data. So we see there the bias and also the error measurements, we calculate them. And then, so we use some selection criteria even here. And among the selection criteria, we use also the personal judgment. So based on the nature of the data and based on the other qualities. And if we decide that this model is a good model to be used, then we go further. Otherwise, we do not consider the model. So if we go further, the first step is to calculate the Pearson correlation coefficient between the real observation and the predictions, so both in sample and out of sample data. And then here, after we consider, let's say, a number of more than 10 models, 20 and more, we decide on the border of the correlation coefficient to be considered. So at this moment, we cannot say that we consider those models which has a correlation coefficient greater than 0.8, for example. So we need a positive correlation coefficient, and the border is decided after we observe all the situation. Then, so we filter from these models those which have a correlation coefficient with the real values greater than the border, which we have made by our personal judgment in this situation. And then we use those models in a weighted ensemble model. So, and we we estimate, the weights using the least square support vector machine. And then after this, we start by evaluating the accuracy of this ensemble model. So if we go, we can go further. So if these accuracy measurements show us that this weighted ensemble model is a good one, then we use it for further. But even here, we need to go back, and I will show you some results. We need to go back and to compare with the basic models we have used at the start, because sometimes it depends on the nature of the data. So if this ensemble model will work better than the classical models or the machine learning models. But in our case, for the monthly time series, it works very good. So this is a correlation matrix. You can see that this is the real data. So this is the energy production. And here in the first row, you can see the correlation coefficients between the real data and all the models, which are here. So the estimated values from each of the model are in the diagonal. And here you can see that the correlation coefficient for some models is, let's say, significant, such for these three models here, and maybe for this one here, which is the last one. And for some other models, it is insignificant. So maybe this is, for example, here, the Auto-ARIMA model is not a good model to be taken into consideration for prediction. So it is even seen here with a very low value of the correlation. So after we choose here, which, so the border of the correlation coefficients, it means that we are taking into consideration these three models here. So we know which they are. And then here, for example, those three models which I presented before. So from these three models, one of them is a neural network model with external regression, which are the three time series. And the other one is an STL and ARIMA combination with ARIMA model. So here you can see, in fact, a residual analysis of our final model. And here are the data. So the black line is the testing data, which we have used for the out of sample data. And the colors here are some of our proposed models. So you can see we have named hybrid 1 and hybrid 2. In fact, there are some literature which says that if we give equal weights to all the models, maybe this will give us a good prediction. And hybrid 1, in fact, is the one, in our case, is the model the methodology we propose. So if you see here, even if it is a very little difference between the weights, we believe that it is important. So it gives more weight to the third model we have taken into consideration. And further, I'm also showing you some results for the in-sample. So for the in-sample data and the situation of our proposed models, and for the out-of-sample data. So if you see, we have taken into consideration the bias of the models and also the root mean RMCA value of the model. And you can see that some of the models, some classical models are away from the, let's say, from the good models. From those models, we can consider a good model. And here, and this part here, we have hybrid 1, so our proposed model, and hybrid 2, which is the model with the same weights. So here is a zoom. So here you can see that hybrid 1 is a model with a bias very close to 0. This model 7 here is in fact a neural network model. And again here for the out of sample data, we can see that both our proposed model and also the model with the same weights for each of the models are performing very well compared to other traditional models and machine learning models. So in fact, what we want to consider, and we are working on it, is to consider, apart the Pearson correlation coefficient, the temporal correlation coefficient, which is used as coefficient in comparing the behavior of two sequences or two time series. So maybe we are adding, at this point, we are adding some similarity measurements to the time series. So just to compare the predictions and also the real values, especially for the out of sample data. So this is our next step. But till here, we can say that the ensemble models with different weights, so giving priority weights to some of the models, can be a good choice to predict especially in the monthly time series and in energy production. So in this situation, it is one of the good models to be used. So this was our study. We're continuing. Thank you.
Thank you. Okay, we have time for, we have 2 minutes for questions.
Hi, Iralda. Actually, I have a short question.
Mhm.
What is the forecasting horizon of your forecasting scheme? It's weeks or it's short term?
We have divided the time series in 80% of it to be used as a training data, and 20%, which means approximately 3 years predictions. So monthly prediction for the 3 years.
Okay, it's monthly prediction. Okay.
Yes.
And every month it's a re-estimation of your model. So you estimate the weights for all the individual models or for the simple models, and then you will get the meta model, I would call it now. Is it right?
So what we do, we start by constructing some models, and then we analyze which of these models can perform better or can give, let's say, a better accuracy in the prediction. So, for example, the AutoArima the SARIMA models are not performing good in this data, so we do not take into consideration it. But the neural network with those 3 external variables is a good one to be used. And also, it was a combination of the exponential smoothing models. This was also good to be used. And so we consider those models which seems to be a good choice for the final prediction. And our task, in fact, and challenge is to decide this weight. So the algorithm will put weights to each of the model based on their performance, so their contribution. So which gives us a more accurate prediction. Mm-hmm.
But is it done one time, also beforehand, and then the model is run, or it's re-estimated every month?
No, as a start, we have done only, so we are at this
Only
part.
once.
Yes,
Okay.
only once. But I believe it would be a good point to re-estimate it and to construct a dynamic model. So
that's, and I think you have enough time. It's on a
yes.
monthly basis.
And so regarding time is over, unfortunately.
Okay, great.
So,
thank you.
Thank you.
Thank you very much.
Actually, I think I'm the next speaker.
Exactly.
Okay, so I can pause the share. Yeah.
So can you see my screen?
Yes.
Okay. First of all, I would like to introduce myself. My name is Jens Klaholczyk. I'm a research assistant at the University of Duisburg-Essen. And I would like to present today our recent work or project, which I have done together with Mikhail Narayevsky and Florian Ziel, which is our supervisor. The topic is outlier detection in water and energy related time series data with a model-based clustering approach. I structured the presentation as follows. First of all, I would like to give a motivation. Why do we need automated outlier detection algorithms? Then I would like to highlight the requirements for practical usage, so that you get an understanding what an algorithm should fulfill to be used in practice. And then I would like to go into depth. I would show you the methodology behind our algorithm. And then I would like to speak about evaluation. It's actually quite difficult. So I'm just showing some example that you get an idea how the performance is of this algorithm. And finally, I will give a short conclusion and an outlook. What might be further steps? Okay, the motivation is as follows. The amount of data collected by sensors and automatic measurement devices is increasing rapidly in the water sector, and measurement or failures in the measurement process are occurring frequently. So an automated or validation process at all is inevitable before we can use the data for data analysis and later for human-based or automated decision making. With a look in the current state on the current state of data validation in water utilities, it turns out that many utilities do not have a validation process at all. So they're using data without data validation and analysis. In the automation, it's a bit different there. They're using rule-based algorithms, but they are usually too simple and really process specific. And there are also some utilities who do cost-intensive and time-consuming manual data pre-processing, and this is actually the reason why we decided to start with this project. And our goal was, and it still is, to develop an automated, purely data-driven, interpretable anomaly detection algorithm, which is tailored specifically to time series data collected in the water and also in the energy sector. Now I would like to give you an idea which kind of data we are dealing with. On the left side, it's an NH4 measurement in the activated sludge process. Here it can be highlighted the negative spikes. They are actually measurement errors. And the water utilities by now have to remove this negative spikes by hand. And this might be an application for an automated algorithm. In the middle, you see the inflow to a wastewater treatment plant. And the spikes who are going up are the precipitation, or go back to precipitation, and they're actually no outliers, but they are really special and make the time series quite difficult to model. On the right side is the water consumption. There you can see a typical daily pattern or seasonality, and it can be highlighted that you have a variance or high variance during the day, and during the night the variance is relatively stable. And the idea is to develop an algorithm which helps to find outliers or suspicious data within all of this time series, which are shown here, and much more. What has to be noted beforehand is that the identification of outlying data is not straightforward, especially if you have no domain knowledge about the underlying process. And even you have more sophisticated knowledge about the underlying process, it's not clearly distinguishable what is outlying data or normal data. So it's a quite tough topic. We have talked with water utilities, and we came to the conclusion that there are 3 points are highly valuable, and an algorithm should fulfill those points. First of all, it should be applicable in real time and on historical data stocks. So the algorithm should be time efficient, and it should handle moderate to large data sets. Interpretability, it's actually really, really important because the human supervisor who's standing behind and has to control the algorithm should understand why an algorithm says an observation is an outlier and why not. Moreover, probabilities should be provided so that the strains of outlyingness can be quantified. And lastly, transferability and robustness is meant that the algorithm can be used for different time series data, and that no labeling is required. So the algorithm should be mainly data-driven, and no comprehensive tuning should be necessary. Based on this goals or requirements, we decided to use a model-based clustering approach. And the idea is that we model the data as a mixture of distributions, and one of these components is intended to collect all the outlying data instances. Okay, now I'm coming to the methodology. We are using Gaussian mixture models. The statistical model is shown in the formula over here. And the idea is that the data is modeled as G, or as a mixture of G components, which have all the same multivariate Gaussian distribution, whereby we allow for some between group variation in the covariance matrix of each component. As I said before, the idea is that one of these G components is intended to collect all the outlying instances. After getting a short idea of the statistical model, I'm going into the depths and showing you all the steps we have done to build up this algorithm. First of all, we have built a feature space. The idea of the feature space is it should help to separate normal observations from outlying instances. And for that, we used the raw data. For illustration, I introduced here two artificial outliers to make it a bit more understandable. We decomposed this series and used the reminder to build up the features. Here we focused on the gradient. So all the features we build are in terms of the gradient. And the gradient is the difference between two time steps. And here the features are shown in a one-dimensional space. And as you can see, the features indicate where they assume an outlier occurs. To get an idea, because we are now moving into a multi-dimensional space, I have here a visualization where you can see it in a 2-dimension. Actually, we have 8 features. It would be normally an 8-dimensional space. But even here, you can see that the data formates in clusters, and the outlying instances marked in red are separated from the rest data. So that's a good basis for the clustering approach. Now I'm coming to the outlier component because we have different time series data, and some of these data sets might not have outliers at all. Therefore, we have to introduce artificial outliers to have a cluster which can or which could collect theoretically outlying instances. We made 2 assumptions. First of all, over this parameter, we control the size of the outlier cluster. And as you can see here in the time series plot on the right side, these are the artificial introduced outliers, and the rest are the normal data. We orientated the distribution of this outlier cluster on the feature space, on the original feature space, and just blow up the covariance matrix and got this distribution over there. After setting up the outlier cluster, we have to estimate this Gaussian finite mixture, and here we use the expectation maximization algorithm. It's quite close to the maximum likelihood estimator, but allows to estimate distribution with latent variables. For model selection, actually, we have to estimate the clusters G and the optimal covariance matrix as well. We use the BIC. And to speed up the expectation maximization algorithm, we use agglomerative hierarchical clustering. The problem with the expectation maximization algorithm is it's relatively slow, but with good initialization values, you can speed up this algorithm. But nevertheless, we have the problem that the initialization is not robust and significantly influences the results of our EM algorithm. Our workaround is we decided to repeatedly carry out this estimation, so it's becoming more robust, but shortened the data set. So we are just estimating on a subsample of the original data to keep the computational time stable so that it can be used in real time. Okay. Now I would like to come to the computation of the probabilities. So for each observation based on the estimated Gaussian mixture model, we compute the outlier, or the probability that this observation is an outlier. And I have here the same example. and the algorithm would give back these values and is indicating that the two artificial introduced outliers have a high probability being outlying data, and the most data points have a probability of almost 0 and a few around 1 to 10%. So we can give back and measure for the level of outlierness. But moreover, we can also give an idea about the cause. Because we have set a statistical model, we can do inference and indicate what has specifically caused a specific observation to be moved to the outlier cluster. And I have here an example. So we have here the feature space, and I grabbed from this feature space one feature. It's actually the relative gradient. And what we did, we moved, well, first of all, we have identified based on the statistical model and the probabilities what are outliers. And those outliers we have moved back to the feature mean. This is actually the yellow time series. And based on this new modified relative gradient, we can compute the probabilities and can compare them. Here it's the probability before the shift to the mean, and here afterwards. Here we have a probability of almost 1, and afterwards it's going to 0. And this is going to indicate that the relative gradient solely caused the outlier assignment. It could also be that an outlier is caused by 2, 3, 4, or 5 features, or even more. The interpretation behind this is that the relative gradient is a feature which is modeled based on the gradient in proportion to the local volatility. Focusing on this data set, it is that the water consumption during the day has a high volatility, but during the night it's relatively stable. And an outlier during the night, based on the volatility, has much higher impact as it would have during the day, because there's much more fluctuation, and it would not, it would not be suspicious. Okay. Now I would like to come to the evaluation setting. As I said in the introduction already, it's not quite straightforward to do an evaluation, a reliable evaluation, because the considered data set is usually unlabeled. So the water utilities do not mark outlying data in their data stocks. And even if they are doing it, it's not always clear, because depending on the field of application, some observations would be outliers and some not. And therefore, we decided, at least for the moment, to just show some examples. And here I have to say that all these data sets I'm going to show are not manipulated. This is the data we got from the utilities. The first example is the inflow to a wastewater treatment plant. Here you can see it's a spike from precipitation. And over there, the algorithm is saying with the red dots that here are, the probability is quite high that here are outlying data. And if we zoom in, we can see that it's a pump play, and it's actually quite true. This is not the normal behavior, and it's because of a failure in the, not a measurement failure, but a failure in the running of the pumps. The next example is of the NH4 measurement in the activated sludge process. Here you can see we have a lot of data which is considered as outlying data based on the algorithm. And after discussion with the person responsibility of the water utility, he could verify that all the spikes going down are measurement errors, and it's correct that the algorithm could statistically separate those values from the original time series. Here on the right side, I have an example of actually the first example for the energy part. It's the solar production, and our algorithm is computing probabilities, a few or just a few with a high probability, and we have a look on it. It's just, or it's not just, it's a solar eclipse. And also here the algorithm has done a quite good job. And in comparison, We have here two algorithms which are mainly, or which are often used in R. And as you can come, the performance, you see that this is quite poor. Okay. Now I'd like to come to the conclusion and outlook. Yeah, first of all, the proposed method stands out as it allows to find outliers in complex time series structures and simultaneously provides a high interpretability of results. So besides the accuracy, it has to be highlighted that this algorithm can also give some description and some ideas behind the mechanism, and this might help the person responsibility in the water utility to better understand why this observation is an outlier and the other not. Yeah, the proposed feature space is actually highly important because it formulates what is considered as an outlier and was not. As I said, we have focused on the gradient. There might be other aspects from a time series which also be interesting. So there can be more work done. And finally, we have to do a reliable outlier detection study to show that our method can beat other competitors. And finally, I would like to recommend the R package TS for PrEP. The package is intended for data pre-processing and data cleansing of a variety of time series data. And actually this algorithm will be implemented there soon. And you can give it a try. Okay, then I would say I'm done. And I would like to thank you for your attention. And yeah.
Thank you. There may be time for a very short question.
So this is Richard Povinelli from Marquette University in the United States. Very nice talk. Could you talk a little bit about the features that you selected? They were listed on some slide. You've got about 8 of them. Could you talk a little bit about them?
Yes, of course. We focused on the gradient, as I said. And for example, you can see here the gradient, the absolute gradient. Sometimes we have the gradient from one side to the observation and to the other. We summed it up. So we have the double size. We have the gradient based on the seasonality. So it's a difference between, for example, 24 hours or the seasonality you have in the time series. We introduced a deterministic seasonality. It's actually, it's just a deterministic increase over 24 hours over the period.
Okay.
It's actually quite easy. But I see Björn.
Yeah. Unfortunately, the time is.
Thank you very much.
Okay.
Thank you. Okay, so the next speaker is myself, actually. So I will start sharing my screen. I hope this works. So it is this one. Okay, can you see my presentation?
Yes.
Great. Okay, yeah. Hello, my name is Björn Sonnenschein. I am since beginning of this year, I'm a PhD student, and I will give you a short report about my current research topic and the first results I do with Florian Ziel. And let's start. I will first give you an introduction and motivation, followed by a description of the system properties and the data set. And then you will learn more about the methodology and the results. So what are we doing and why are we doing this? Oh, okay, it works. The motivation is that we all know that wastewater treatment is really important, but the process of wastewater treatment is quite sensitive to the inflow at the wastewater treatment plant. And so it has to be controlled continuously and has to be adapted according to the current inflow rate. And the problem is that the system is quite slow to react on control changes. So if we notice that there's rainfall and then the inflow raises, then it's already too late, basically, to adapt the control. And therefore, inflow forecasts can provide a benefit because it enables us to do proactive control of the treatment process. So the objectives that arrives from that are that we want a forecast horizon of approximately 2.5 hours. That's the reaction time of the system in the worst case. We want to focus now on the inflow increase in case of a rainfall event, because this is a critical event. And we want to choose a data-driven approach so that we have a short runtime and can transfer the algorithm to other networks. And we want a probabilistic forecast because human have to deal with the results and have to do it as a base for decision making in the process. Okay, so this is a motivation, and let's look at the system we have to deal with. Yeah, the system properties, we have a sewer network, which is a network of pipes which collect water, wastewater, and then they carry it to the wastewater treatment plant. And that means that the flow rates we measure throughout the network at remote locations provide some information regarding the inflow we have to expect at the wastewater treatment plant once it arrives. But this only works in the time horizon of the dwell time, right? So, and this is the first problem we have, because the dwell times are actually dependent on the flow. So especially at rain events, rainfall events, when it's the flow is really high, the dwell times decrease to maybe minutes. So really not much information from the external measurements here. So we need a rain forecast. And it also means that we have huge nonlinearities in the system, because these dwell times are flow dependent, and therefore the temporal dependency structure is also flow dependent. That's the first problem. And the second problem is that we have detention basins in the network. And this means that water is also buffered and even removed from the system. So let's take a look at how this reflects in the data sets. Our data is from a German wastewater treatment plant. We have data across 3 years, historical data. And our variables are, on one hand, of course, the wastewater treatment plant inflow. This is our target variable. And then we have external measurements. We use 4, which are distributed throughout the network and measure the water level in the pipes and in the nodes continuously with a resolution of 15 minutes. And we have also got local rain rate measurement, and we have historical radar rain data. And from this radar rain data, we performed some baseline radar forecast using optical flow extrapolation, just to provide a really basic forecast and see how our model deals with this. But we focus on really the historical rain rate. We use this as an oracle future to assess how well the model reflects the dependency structure in the data with a perfect forecast, weather forecast. Okay, so once we can take a look at a qualitative look at the data itself, and on the right-hand side we have 2 days of data. The top is the wastewater treatment plant inflow. Below this, you see the external level measurement from one station, and below is the rain rate, and we see it is a dry day, so no rain at all. And we can see that there's a strong periodicity throughout the day. This is the dominating feature for dry weather. And we can also see that there's a certain lag between the level measurement and the inflow, which is good for us. We see this is the dwell time accordingly. And we also see that there are some spikes here that correspond to the somehow propagate throughout the network into the inflow. And on the left-hand side, you see a histogram over the periodicity, and we see here's some split at 8 hours in the day, and this mainly corresponds to the day of week effects we observe. And we see many high values here, and this cloud, that's the stuff that's problematic for us, because these are the rain events. And so let's take a look at how the rain events look like. Here we see data for a rainy day. And on the right-hand side, we see the same as before, but with the measured rain rate. And we see there's a short peak of rain. And from this follows a huge and steep increase of inflow. And this is then followed by a period of near constant inflow, which is caused by buffering in the network. And then if the buffers are empty, then the inflow decreases again. And this constant phase can be several hours, and it's dependent on the previous rain volume. And we can see that this is not a black swan event, but rain really happens often, and we reach the capacity limit quite often. So this is what we have to deal with. We have to deal with the linearities arising from the rain and the high inflow levels according to this. And so let us take a look at how we deal with it in the model. We model the full predictive distribution for the inflow. This is YT. And we model this as a Johnson's SU distribution. This is basically a transformed normal distribution, which gives us a bit more control about further shape like skewness and kurtosis. And each of this, for each time step, each of the 4 parameters of the distribution are dependent on the data. And the dependency of the data is modeled first by a linkage function, which ensures that we can map our estimate of the parameters into the valid parameter space of the individual parameter. And then what we have to care about now is these 2 terms here, A and S. And this is, A is an autoregressive term, incorporating the external measurements, and S is a seasonal term. So let's see how what this looks like. The autoregressive term is basically an autoregressive process with external variables, and with one addition, and this is thresholding. This means we have a linear combination of each leg for each feature, but we also consider different sets of legs for different levels of the data value. This is shown on the right-hand side here in this chart. We see some variable. Let's say this is the inflow, and a background boxes indicate the parameters for individual thresholds. And we see here, these are not thresholds from the data. This is arbitrary to illustrate. This is, we see that on the x-axis, it is a leg, which means left 9 is 9 time steps before present. 1 is 1 time step before present, and we basically want to predict 0 and the next time step. And we see that high values of inflow are only important throughout the first legs. This means that the dwell time is really short for high values, and we account for this, that the dependency structure in the time has changed, and for high values they only account for really fast and quick changes within the future, within short forecast horizons. And according to this thresholding, which helps us to model the flow-dependent leg structure, we have seasonal effects, but here's nothing fancy. It's just really intraday seasonality with respect to day-of-week effects. And we also added monthly seasonality to model the seasonality throughout the year. And here we observe that it's better not to add it in an additive fashion, but instead scale the intraday seasonality by the monthly seasonality. So it's like the niveaus spread instead of shift. And this delivers better results. Yeah, there's one interaction term to ensure that the seasonal effects do not apply anymore if we are in this constant phase of high inflow, and that's basically it. Yeah, and so that is the model itself. We have thresholding and we have seasonality that are the important aspects. And so how did we do parameter estimation and implementation? Really a short note only. We have many features, so we use Lasso for regularization and feature selection, and we optimize using Adam, and we use Python and TensorFlow probability for the implementation. So then let's take a short look at the results. What results do we consider? We performed in-sample and out-of-sample prediction, but we will focus on out-of-sample prediction performance. And there we used two deterministic scores. It's mean average error and root mean square error. And we also incorporated the energy score as a probabilistic score, which helps us to assess how the actual distribution is predicted, and not only the mean and not only the expected values. So, and we focused on different cases in the data, right? So I said we have dry periods, we have also periods of rain. And so we separated the data, and we do separate scoring for dry weather periods, the periods where the inflow rises, which is really important, most important in practical terms, and then the time of constant inflow. And yeah, I've also implemented two benchmarks, but please take them with a grain of salt. This is really just preliminary, because this is, I didn't have much time, to be honest, to deal with this. But we will take a look at the comparison. And on the right-hand side, we see a sample forecast at the top with the best fit model. And the table shows us results for different configurations of the model. Okay, so this is really over the whole data set, not for this individual periods, but for the whole data set is going. And we see the first two are models which only incorporate the treatment plant inflow without external measurements. Then we have a model with external measurements and the inflow. And then we have two models which have treatment plant inflow, external measurements, and the rain forecast, the perfect rain forecast given by the Oracle. And then we have our benchmarks. And what we can see as a pattern is generally that the external measurements provide an improvement. These are the external flow measurements in the network. And the rain forecast provides further improvement. And in this case, also the thresholds really help to improve the point forecast as well as the distributional forecasts. And also the LSTM, which is a recurrent neural network flavor, provides quite well. And the bare-bone autoregressive effects with seasonal components and external measurements, which is only linear, cannot handle the nonlinearities well. And let's dig a bit deeper into the details of different periods. So we have dry weather. And in the dry weather case, we can observe that a huge improvement is achieved by adding the external regressors, which is what we anticipated, because the flow that will eventually arrive at the treatment plant can be predicted by the external measurements. And we can see this here in a short animation. So just look at this peak on the right side. This is not predicted well in the long term, but as we come to near to the dwell time of the network, then we see that the prediction adapts to this feature and predicts it quite well. And also the uncertainty there reduces. And the same for the feature here on the right, it's also fitted better. So that much to the dry weather. And then let's take a look at the really interesting phase, because this is where we need it in practice. The prediction, the transition phase, and this is a transition after rain event, and when then the inflow raises steeply and then gets constant. And here we see that basically the model without external information, with only the treatment plant inflow, it fails to predict, because there's just no information about the future inflow rates. And it's a bit better with the wastewater treatment plant flow and the external measurement, because it gives you a really short, for a really short time frame before the rise, it gives you some information, maybe for 10 or 20 minutes. And then we see that with external rain, with the rain prediction, it's really is a huge improvement, and also the thresholding really helps to manage the nonlinearity. And what's a bit surprising, I guess, is that the purely linear model Also the SARX model also performs quite well. But this is a bit of an illusion, because this depends on how we selected this data time frame. We selected data from around 2 hours around this increase of flow, and this SARX model really fails to predict the rise of inflow, but it predicts the constant phase almost perfectly, because it resembles always to the last known value for high inflow values. And this means the SARX model, even though it does not perform well in this inflow wise, it just outperforms the other models in the constant phase. And this is also visible here. It also influences the scores. Yeah. So let's take a bit deeper look at the temporal structure of the forecast. And there we see on the x-axis is the time step around the inflow increase. So this is basically all rain events averaged, and we see how the models perform at the beginning, middle part, and the end of this time step of the increase phase. And here we see, as I said, the SARX model performs well. It's a green line. It performs well at the end of the phase where it's constant, but it does not perform well at the beginning of the increase. And our best fit model performs well for most of the time, whereas for the external measurements without rain forecast, we really see that it is this line here. It is not good at all, but it tends to be a bit to improve a bit once we are really near or close to the time point when the inflow waves will occur. So, okay, I'm almost finished. Let's skip this. One note to the rain forecasts. If we do not use the oracle, but the rain forecasts, which are really basic, then we can observe that it works well. Of course, if the rain forecast is accurate, but our model is still, unfortunately, quite sensitive to the magnitude changes in the rain forecast, and it's really important to have a good rain forecast in order to predict the inflow raises, which is natural because we need information about further inflow in some way in order to achieve a good forecast. Yeah, we can also see the scores, and yeah, that's basically it. We handled the nonlinearities by a thresholding. That's the important point for us, and we predicted the full predictive distribution, and we see further improvement chances for complex rainfall structures and for incorporating good rain forecasts and also adapt the model to the weaknesses of the rain forecasts. Okay, that is it. So thank you. Here is the literature, and thank you for your attention. I will switch back to Zoom. And oh yeah, we are already run out of time. So I guess that's it. And the session will be closed soon. So thank you. And Zoom somehow disappeared here. Oh, yeah, okay. Sorry, I have technical problems. My Zoom window has disappeared completely, and so I will just say goodbye and thank you.